Hello class, today we're going to look at 15.5 in your textbook, the Binomial Theorem. So first off, we're going to start off by looking at this consideration of a plus b raised to the nth power. We'll be utilizing this setup for the majority of this video. So we're going to start off by simply stating, okay, let's see how we can apply this and expand some terms out. So I have four different examples for you to try out, and I'm going to want you to do each one of them and make sure that you're doing them step by step and keeping consideration of what's inside the parentheses and what's not. So pause the video and make sure you make this attempt now. So you should have the following setup, and we want to make sure to remind ourselves that, let's say for a plus b squared, that it is not equal to a squared plus b squared. That's not true, and you should have definitely set it up the following with your set of parentheses, like so. Remember, this a is going to distribute to a here, and b to a, and b to b. So we're going to pause the video again, and I'm going to write out those steps like you should be doing as well. So I have all my terms listed now, and if this was a huge stump for you, don't worry, this did take me a few minutes as well. Take your time with it and make sure you're doing it all. But remember, you're having your a and your b distribute to each and every term, within their own respective parentheses. So in this case, I have a squared plus 2ab plus b squared, and here I have a cubed 3a squared plus times b plus 3ab squared with b cubed, and so on and so forth. Down here, a to the fourth 4a cubed times b plus 6a squared b squared plus 4a b cubed plus b to the fourth. Now let's see if we can rewrite this in a different fashion. If you did this on your iPad, feel free to copy your outputs from all of these and put them in order. We're going to try to list them cascading down for 1, 2, 3, and 4. So on this page I've listed everything out, noting that this is my first row, second row, third row, fourth row. And I want you to take a moment to see, I'm going to start inputting a little bit more clearly all our coefficients. So I'm going to note this here. That's 1, 1, 1, 1, 1, 1, 1, and 1. And I'm going to also get rid of, for a moment, I'm just going to take everything out in terms of anything that's not a coefficient, just for a second, so we're going to see what it looks like. Now with everything else erased, we can actually start seeing a little more clearly that we have actually some sort of pattern going on. We actually have this cascading 1 going all the way down. Here, I'll draw this on this side too. While the inside, well, we have 2 here, and a count to 3 here, and a count to 4 here, and we have a 6 in the middle. We're not sure what that 6 does yet, but we'll see it in a second. I will state and just simply tell you that actually the pattern does continue, that if I go down the next row, the next one is going to be a 1, the next one will also be a 1 on this side, and that this will simply be 5, and it'll be 10, 10, and 5. And that you actually have another count for here as well. This is the 5th row, and we still have 1s on our outside. This array of values is actually so important that we typically refer to this as, most commonly termed, Pascal's triangle. And it is very important and related quite simply to the binomial theorem, which we're going to derive in a second. For Pascal's triangle, we also refer to these coefficients as your binary. Did not write that correctly. Binary coefficients. I want you to try to also make an attempt to see if you can see the next level of the pattern, aka what is going to be our 6th row. So this was our 1st, 2nd, 3rd, 4th, and 5th. I want you to take a guess on how would you guess the 6th row. So take a moment, try that, and see what you get. So this is what you end up getting. And you may think, oh my gosh, I don't even know how you even got that. That's amazing. I know, that's exactly what you were thinking. This is just absolutely incredible. But actually what you're just doing is taking these coefficients and adding them together to get, the preceding coefficients to get your next row's coefficients with, ones on the outside continuously to cascade downwards. Now I'm going to take the sixth row and see if we can actually see mathematically what type of pattern we can do. So with the sixth row listed, we actually can simply see that there's a pattern that actually exists with our combinations, if you remember your combinations formula. I'm going to simply denote that as 6C0, 6C1, 6C2, 6C3, 6C4, 6C5, and 6C6. In this next step, I'm going to write out what these all look like. Now here it all is all written out, and don't panic. This did take me a while to write out, and it's fine to take a while, but I'm going to simplify this further. So if you need more time, like I said, please feel free to pause the video. But you're going to be left with 6 factorial over 6 factorial. This one's going to be simply 6 over 1, because the 5 factorial will cancel out most of the 6 factorial. And this one here is going to be 6 times 5, canceling out most of the 6 factorial, over 2 times 1. This one here is going to be simply 6 times 5 times 4, over 3 times 2 times 1. And so on and so forth. But you actually note that after this middle term, this setup here, we're actually going back up. That in this case, we're going to have, again, 6 times 5, because now this side started getting larger, whereas it was getting larger all the way, and this term here was becoming lower and lower, but now it cancels out our other terms again. We're actually left with 2 times 1. This one's going to be 6 over 1, and this one's going to be 6 factorial over 6 factorial. And we end up simply reducing all these to 1, 6, 30 divided by 2 is 15, and we have 30 times 4, that's 120, divided by 6, that'll be 20, and then 15, 6, and 1. So we can actually see that as our rows get more and more, as we start adding rows, we actually can get all these coefficients simply by considering this count of our combinations, as in our number of terms and our choices for how many terms we have, how many potential options we have, and doing the combinations of how many outcomes exist. And this goes all the way down, and that will give us our leading coefficients. So with this formula, we can now say that any binomial term for a plus b raised to the n will simply be a count of nc, the combination, 0, multiplied by this whole term here, which is a raised to the n and b to the 0, plus, and now we start counting up, nc1, a, n minus 1, because that one has to count down, and b raised to the next one, so on and so forth until you reach the n, the final count for n, and a raised to 0, because now that one was decreasing, and b raised to n, because that was the final term that we have. So overall, this is our final formula for the binomial theorem and Pascal's triangle. So how is this helpful? Let's try it out in an example problem. So expand the following: x plus y raised to the 4th. Now you could do this out the long way, or you can be taking a slightly more easy way out by simply using our theorem we have from before. We know that our first term of this is going to be 1, and our last term will be 1. So now, with this, we also have x to the 4th and y to the 4th. Oh, let me move that over. And now we have to fill in the rest. Now we have been writing, in this case, using c's But you can also write it in terms of the following, using this notation of your total number of terms being in the top part of this matrix. So that would be in this case 4, and your choices here below it being 1. And in this case this would be x n minus 1. So let's undo that. So this would be 3, and this y would be 1. I think I realize I may need more space, so I'm going to move this all the way over. So keep going. I add this 2 next, saying 4, 2, x squared, y squared, plus 4, 3, x, y to the y cubed. And now I have nearly my full expansion. I still have to simplify these, wrong one, these here. And if I were to rewrite this, I am going to write this as x to the 4th, plus in this case 4 x cubed y, and I don't need the y to the 1, plus in this case that this is going to be 4 factorial over 3 factorial, oh sorry, 2 factorial, looking at the wrong one, 2 factorial multiplied by 2 factorial. And I'll keep going through, say x squared, y squared, plus, in this case we already know this is going to be 4 again, xy cubed plus y to the 4th. Simplify this further, x to the 4th plus 4x cubed times y, and this is actually going to reduce to 6, x squared, y squared plus 4x y cubed plus y to the 4th. And this is your expanded binomial. Sorry, I should say your binomial expanded. Overall, this will be quite helpful in terms of simplifying how much you would have to write all this out in terms of expanding this, and also if you had to plug in, let's say, values in for x and y. So if I were to write out x equals 10, let's make it easier, let's make it 2. Erase that, undo, let's go 2, and y equals 3, we can just simply plug that into this here and get our values. Overall, I know this may have been a confusing lesson, but I'm hopeful that you took notes, and we will go through a worksheet in class to review concepts and other ways of applying this theorem. I hope you overall enjoyed the lesson, and I will see you all again real soon.